So, Gordon, please.
Okay, thank you. So myself and my two compatriots here are going to give an introduction to the discussion. And mine is going to be a very introductory, maybe an introduction to the introduction, in which I will pull you a little bit out of the theme of the conference and just talk about quantum field theory with not much to do with gravity for a while. And Andrea and Geoffrey will pull you back to where you've been in the last while. So I'd like to talk a little bit about some work that we did on infrared divergences. And this is very related to the subject of soft hair, but I'm not actually going to mention soft hair. I will let my colleagues tell you about it. What I'm going to do is I'm going to review the infrared problem a little bit in quantum electrodynamics and perturbative quantum gravity, and tell you something about our work, which was to revisit this old problem and look at it from a slightly more information theoretic point of view. So let me begin at the beginning. So quantum electrodynamics, I remember as a graduate student reading a review paper by an eminent theoretical physicist at the time, who said that quantum electrodynamics is an exactly solvable field theory. That's because its coupling constant is small. It's known how to renormalize it. And so by calculating some orders, you can derive numbers which are as accurate as you will ever need. And in some sense, that's true. So for example, the Feynman diagram for Mahler scattering, an electron from electron, should give an accurate answer for the amplitude for that process to about a 1% level, because its correction, of course, has a loop diagram in it. We know how to subtract the ultraviolet divergences and make this a renormalized perturbation theory, and this should be down by a power of the fine structure constant, which really means a correction of order 1%. And you go away very happy with that when you learn quantum electrodynamics and then basically forget the subject and go on to more interesting things. But if you read a few chapters later in the quantum field theory textbook, there is a bit of a subtlety, and that's called the infrared divergence. In a loop like this, there's not just a divergence from the large momenta circulating in the loop, there's also one from small momenta, which actually makes this logarithmically divergent. And the way that is dealt with is to go to the level where you calculate probabilities and not just amplitudes, and add to it the amplitude for emission of a soft photon. So this should end up the same order in perturbation theory. And then the cross term, when you calculate this square, should cancel the leading term here. And that's guaranteed by unitarity, and in fact guaranteed to generalize to order by order in perturbation theory. And this is the age-old way of taking care of the infrared problem, which dates back to the early days of quantum electrodynamics, even before it was known how to take care of ultraviolet divergences. The infrared divergence in here, though, has another subtlety, in that it makes this contribution actually bigger than this one because it's logarithmically divergent. So you should really put a cutoff, and should keep the cutoff far away from the limit you want it to be. So this is small and perturbative and cancel things. On the other hand, if you take the cutoff small, this becomes big. And in fact, diagrams with more infrared divergences even become bigger. And at the end of the day, there is a statement that, well, these have to be compensated by things like this. So a photon emission, there is a statement that the processes that actually dominate the amplitude have infinite numbers of soft photons coming out of them. Look something like that. So in inclusive probabilities, these soft photons, of course, cancel against infrared divergences. So mathematically, the right thing to do is this, if you want the leading order. But physically, what is said to be happening is this, that it's splaying off a bunch of soft photons. So there's one interesting question which comes to mind when you see this. Okay, so these soft photons are supposed to be, well, really soft, too soft to be observed by a detector. So in a sense, with wavelengths and frequency smaller than a detector resolution. So in your experiment, they escape detection. They fly away from your experiment undetected. And so there's a rather, they also, I should say, have, well, it can be organized so they have too little energy, in a sense, to affect the kinematics of the experiment. So you don't even detect them by missing energy or missing momentum. There is, though, a natural question, and that is how much information do they carry away with them? So this is a conference about information, and that is sort of an interesting question. A soft photon, well, it does have some attributes, helicity, a direction of propagation, and so on. So it takes some information to specify its state. So how much information does it carry away? And in a more quantitative sense, is there a quantum correlation between the soft photon cloud that flies away and the hard stuff that's left behind? And one could do that by calculating the entanglement entropy. So try to compute the entanglement entropy of the hard things in the scattering process with the soft photons that fly away. And it's a fairly straightforward perturbative calculation. And what one finds is that the entanglement entropy itself is actually infrared divergent, which means that the soft and the hard are highly correlated, and that the problem is non-perturbative. That if you find an infrared divergence which doesn't have can't be canceled in the leading order, it really means one should calculate higher orders and resum and understand what that does. Well, when you resum this infinity, it turns into an exponential of minus infinity. So infrared divergences in perturbation theory turn into, when they're resummed, zeros of certain things. And what they turn out to be here is zeros of certain off-diagonal elements of the density matrix for outgoing hard particles. In other words, decoherence.
Sorry, question?
Yes?
The splitting of the Hilbert space you're doing here is not spatial, right? This is sort of a field space.
It's really in field space and in momenta. Because I could have also hard photons, which I wouldn't be tracing out. Right? So it's in momentum space and in fields. And it's right, it's not local. And non-locality will dog me for the whole time here. Because, okay, so the lesson of this story, which I'm not going to have time to write formulas for you, are highly correlated or are entangled, and that leads to decoherence. Well, maybe a little bit, just a little bit of a formula. So if I have an incoming state, let me just talk about K for hard particles. Let me write it as an incoming density matrix. It evolves in a scattering experiment by the S matrix, which conventionally usually is stuck on the density matrix like this. to an out state, which is a superposition of incoming states. And so that out state might have some hard momenta and then some soft stuff. And we can generally look at any component of the outgoing density matrix. So it should look something like that. Now, these things have to be calculated with an infrared cutoff. This S matrix has these things in it, but this other stuff hasn't been done yet. So it needs an infrared cutoff to make it finite. But generally, a hard incoming state will produce hard and soft stuff. Then the way we solve the infrared problem in this language, the way we do this is we trace over the soft stuff to make a reduced density matrix for outgoing hard stuff. Then the diagonal components of this hard, or of this reduced density matrix, I should say, if you put L prime equals L, just give you the probabilities that particle physicists have been calculating forever, and which I have nothing, zero, absolutely nothing new to say about. The off-diagonal elements, however, are these things which feel the correlations between the soft and the hard, and in fact, which the density matrix itself is a thing that you would plug into, say, the entanglement entropy to calculate how entangled the hard and the soft are. So this turns out to be infrared divergent. And then if resummed, one can actually apply soft photon theorems to these various matrix elements, as well as the sum over soft stuff. What happens is you get ratios of various cutoffs. So let me draw a graph of cutoffs. So here's 0, and this is photon frequency. So a fundamental cutoff. And then some cutoffs of convenience, which there will be two. One is a cutoff for internal, the photon momenta in internal loops, and the other is a detector resolution, and they can be around the same magnitude. And so stuff up here is hard. Stuff in this interval is soft. Below here is non-existent. And so in a sense, this is what defines it. So when you compute this using soft photon theorems, from this and this, which contains, say, the cutoff on loops, and the fundamental cutoff, you get something like this. You get that this is equal to this same matrix element where S is computed with a cutoff different from the fundamental one, say a cutoff of convenience. In a sense, you get a renormalization group-like formula which tells you how to change that cutoff. And the validity of this formula depends on having actually a fairly strict hierarchy between hard momenta, which are up here, these cutoffs, and this one. Okay, so one can extract the cutoff dependence of the S matrix elements using soft photon theorems, and they look something like this. So these numbers up here depend on, and one can get one for each factor. Then the trace over soft photons also can be summarized by a factor. That's kind of soft photon theorem number 2. And so one could get rid of this, all reference to soft, all reference to cutoffs, by including a factor which is like fundamental cutoff to a detector resolution, again to some numbers which depend on the kinematics of the hard particles. And these numbers, well, the formula is fairly unenlightening. I'll write it for you, but indeed this is what happens. So you get these factors times just the S matrix elements for hard stuff, as if there wasn't a soft sector at all. Then, if you want to put the photon mass to 0, or get rid of the fundamental cutoff, you have to address the problem in these two factors. And it turns out for diagonal elements, when L prime equals L, and these two, which are written the same, are indeed the same, these exponents turn out to be the same, and the fundamental cutoff vanishes, and what's left is lambda divided by lambda tilde to some exponent, and that's just the usual Sudakov factor, which has the detector resolution, for example, sitting in it. For the off-diagonal elements, generally these exponents don't cancel. Generally this adds up to the fundamental cutoff to some positive semi-definite power, and the exponents only cancel when that power is 0. That power will be 0 when the currents, here I'm talking about the electromagnetism, in the two final states, the two legs of the density matrix, the actual electric currents for electromagnetism. So if there are n hard particles, it looks something like this. So for one of the states, it could be a set of electric currents like this. For the other one, the same with primes everywhere, when those two sets are actually identical. So you get a huge decimation of the outgoing density matrix, which basically amounts to decoherence. Okay, so that's, in a sense, result number 1. This can also be done for perturbative quantum gravity. Almost everything I said goes over, with some small differences. I might not so confidently impose cutoffs. I'm not sure quantum gravity has a, well, I don't know, sensible, for sure, covariant infrared cutoff. So there are subtle issues there. In QED, of course, I can give the photon a small mass. That's a nice unitary cutoff. The theory is still unitary, if not gauge invariant. And so I can use a photon mass as a fundamental cutoff. In gravity, maybe not. I'm not sure. So I'm at a bit shakier ground there. And also, of course, quantum gravity isn't a renormalizable field theory, so it would have to be thought of as an effective field theory of some sort. On the gravitational side, instead of these things being set equal, it's actually energy momentum tensor elements, in a sense. Single particle ones that are set equal by this condition.
So what is the, just remind, what is set equal to what? It's the incoming and outgoing momentum?
No, it's this thing for the two legs of the density matrix.
Ah, okay.
Okay, the outgoing density matrix.
Right, okay.
Okay, so that kills off elements of the outgoing density matrix, and that you call decoherence. And then for gravitons, it's basically the energy momentum currents rather than electric currents that are set equal. So for processes with a few particles, this can basically diagonalize the outgoing density matrix. Okay, so, yeah?
Yeah, when you say decoherence and diagonalize the outgoing density matrix, so that's in some particular basis.
Yeah.
Is that just the basis for definite particle numbers and momentum? Or?
Yes.
Okay.
Yeah, so the pointer basis is the one where the currents are diagonal, which is the same as momentum diagonal. Okay, so that's number 1. Now, this picture has some problems. For example, I could reverse this. Say I want the same out state but different in states. Get basically a similar result. That this is 0 unless the currents here are the same. For simple instates, that really means the states are the same. And that poses a fundamental problem with trying to do interference experiments and so on. In fact, it's quite a bit more dramatic. And so there seems to be a fundamental decoherence in this picture. It's probably not as dramatic as I make it sound for the following reason, that for any field theory, actually, the S-matrix approach is a idealization in a sense. You never really do an experiment with in a way that follows the idealization, where you really sit infinitely far away, send in particles, wait an infinite amount of time for them to scatter, and so on. In a real experiment, these infrared cutoffs would likely be replaced by, say, the inverse time it takes to do the experiment. And that can be long in fundamental physics units, but we're talking about logarithmic divergences, which grow slowly. And so in a sense, that puts a cutoff on this procedure, which is a lot more difficult to estimate, and perhaps puts the fundamental decoherence here at the edge of what's observable. Okay, let me say a few more things. I'm probably running out of time here.
Actually, how much more time do you need?
Maybe 5 minutes. There is a second approach to this, and that's to modify what you mean by an in and out state, to go to so-called dress states. So here, so far, I'm talking about Fock-space photons and electrons. But in a way, there is, in some sense, a way to subdiagonalize the density matrix. Not the density, the S matrix. And the way to do that is to notice that in a process like this, in a sense, the radiation that comes out, all of these things, are peaked in two directions. The direction of the incoming stuff, and that's these photons, and the outgoing stuff, that's these photons. What the dress state is to simply take all of these photons that are peaked in the direction of the outgoing stuff and call that whole thing an electron. And then the incoming stuff, what you do is you add a whole bunch of photons to it. In a way, you make it look like this one. So a whole bunch of finely tuned photons to look just like this one. And what their role is to cancel out to do destructive interference with all of these and cancel them out. So in that picture, you don't actually have extra photons. What is more, that picture can be obtained by a canonical transformation of the Fock space. So it is a bona fide way to go. In that picture, actually, with the canonical transformation, well, the electrons, positrons, and so on are redefined this way. The other thing that happens is, of course, the photon field gains some classical part. Classical, not really classical for some distribution of charges. What it really is the far infrared tail of the Leonard-Weikart potential for the currents that are in the state that you're talking about. Okay, in fact, I can write the let me write down the thing that generates the canonical transformation, and then I'll be done. So for some distribution of electron momenta, the thing that generates the canonical transformation is this formally unitary operator. So here I have a sum over the different incoming particles and the helicities of the photon. see, and upstairs is... And so this is summed, then there should be a charge of each particle here, and then a photon creation operator with the helicity should go here. And then minus Hermitian conjugate to make this a unitary operator. So simply operating this on a state which has charged particles with momenta p creates the so-called dress state. It also has photon creation annihilation operators in it, so conjugating the photon does this to it. So in this picture, in a sense, it describes a process like this more efficiently. In the limit where you remove all fundamental cutoffs, actually this is not a proper unitary operator. Right? This is a well-defined canonical transformation, and the commutators map to commutators, but the operator itself doesn't really have a domain. So in that case, once you do this transformation, you should never again mention single photons or Fock states of electrons. Should always work with these dressed particles and the photon which has a classical part. Even before one removes a fundamental cutoff, this is probably a more efficient way to describe things because the cutoff dependence, if it's small, will make these the more important amplitudes. Okay, one still has Fock states and so on in the same Hilbert space. Their overlap with these things are small, with the dress states are small. They scale to 0 with the photon mass, but still non-zero. But if you really have a massless photon, then you're stuck with either Fock states or dress states. You really, or generalizing quantum mechanics somehow to live in larger Hilbert spaces, or larger, I guess it's a von Neumann space of some kind. Anyway, that's the story. In this case, there isn't any decoherence because the infrared, well, soft photons aren't produced here. In a sense, the infrared decouples in this other basis. So that gives us two descriptions of a fundamental theory. Especially when the photon mass is 0, these are really inequivalent. The interesting thing is, perhaps they could be distinguished by some interference experiments that search for fundamental decoherence. And I would say the difference is just completely open. Fundamental decoherence maybe proceeds slowly in the real world. Really, these exponents are small. They have the fine structure constant in them, which makes this decoherence rare. It would be interesting to look for it. And just as a final word, there's probably a third way here. And that is to actually give up on pure states altogether. There's a theorem due to Kinoshita, Lee, and Nauenberg, which is used for non-abelian gauge theories where this doesn't actually work. And there you have to average, in a sense, over degenerate incoming states as well as outgoing states. So if I was talking about massless Yang-Mills theory, like n equals 4, where I should be able to set up a scattering problem, and I wanted to solve the infrared, I would actually have to do some inclusive sum over incoming states too, which means that I'm really assuming the incoming state is a density matrix. Right? It has the hard stuff, and then all possible distributions of soft gluons, in that case, appropriately normalized. And that is presumably the only way to cancel infrared singularities there. And that would also be a third way here. I believe if one in a sense, had incoming density matrices. One could, in the appropriate ones, the infrared and the hard particles are uncorrelated. You can write a density matrix so they're uncorrelated. They still become correlated, and there still will be decoherence in the process. And so that would be a kind of a hybrid of the Dress state and the Fock state approach. So there's probably a third way, but there's been very little work on this third way. So what I have to say about it is incomplete at best. Okay, so.
Okay, yeah, we should continue.
Yeah.
Thank you.
Okay, so I'm supposed to sort of pull you back to the topic of the workshop. I should take this one. But I'm still going to reside in the infrared, and I will not talk about black holes. I will leave that to Geoffrey. I was asked to talk about the relation between different topics in infrared physics. Gordon talked about soft theorems, or soft physics in quantum field theory. And this topic has, in recent years, been related to other topics in infrared physics, which is asymptotic symmetries. The problem is my shirt goes the other way, so I cannot really tag it correctly. So, okay, does it work better? Okay, asymptotic symmetries on the one hand, and then memory effects on the other hand, which I believe will be important for what Geoffrey has to say. And people have called this relation the infrared triangle, for obvious reasons. Good. So, since this is a discussion session, there should be a lot of sort of interaction, and I can make this a bit modular depending on what the interest or the knowledge of the audience is. So I will maybe start by just briefly giving you some facts and what things are related, and we can then go into more detail. If that's all right? Okay, so let me start here. So let me first write some formulas. So let me focus on QED and gravity. And so what Gordon has told us is that soft theorems tell you, so these are universal properties of scattering amplitudes, it tells you that the S matrix with an insertion of a soft particle factorizes into a hard part without the soft particle and a soft factor. And so you can write down explicitly what the soft factors are. So let me just write down some formula. We already had this. So there will be a sum over all hard states, the charge of the hard states, the moment of the hard particles, and the polarization, plus minus. And then there's a soft pole. So this is the leading soft photon theorem, or the soft factor for it. Then we have gravity, where this is essentially replaced by another momentum. Dotted into the polarization tensor. And again, there's a soft pole. Oh. And then in gravity, there's also a subleading soft theorem. This is still 0. Where now one of the momenta is essentially replaced by angular momentum. dot it again into the polarization tensor. And so you see here, this is a subleading soft theorem because it goes at the lower power of the soft particle. And maybe I should have said that the momentum of the soft photon or soft graviton is q, goes to 0, and it's characterized by this. Okay, so this is one side of this triangle, and it has been related to corresponding objects on the other side of each of those corners of the triangle. So let me then briefly talk about this side of the triangle, asymptotic symmetries. So what do you do here? So if you want to write down the asymptotic symmetry group, what you do is you look at all the possible diffuse or gauge symmetries that are consistent with some boundary conditions that you choose, modulo the trivial ones. So you want to look at boundary conditions that are strong enough so that you only keep sensible physics, but it should be weak enough so that you have all relevant possibilities. Okay, so let me do it like this again. So let me start with electromagnetism. So what you do there is you impose suitable boundary conditions on the gauge field by imposing that energy flux is finite, it's a finite charge configuration, and then you get that the residual symmetries that are allowed are ones where you have a gauge transformation parameter that is a function of the angles to leading order. So this is what's allowed. For gravity, this is a bit more tricky, as we all know, because of the intricate analysis by BMS and all the subtleties and confusions that arose. But if you go through with this analysis by imposing finiteness of fluxes and so on, you find for gravity that there are some large diffeomorphisms that respect the BMS boundary conditions, which at null infinity take the form of a function f, and then some translation. And this residual diffeomorphism that is consistent with the BMS boundary conditions is one where this function f is again a function of the angles. And then you can go beyond this and look at subleading orders. And then you find, again, residual diffeomorphisms that are consistent with the boundary conditions, with extended BMS boundary conditions. And there's a function that is, again, a function of the angles. And now what's the relation to soft theorems? So if you impose antipodal matching of these functions across, when you approach I0, spatial infinity, from future and past null infinity, then you impose that these are matched asymptotically, and then you find charge conservation laws. So here you will find that the electric charge is conserved at every angle. So at future null infinity and past null infinities are equated, and that's by the virtue of this matching condition at I0. So these are large gauge transformations.
Actually, a question on that. That's a place where, well, maybe there will be some further discussion.
Yes.
I guess I should use it. But, is there really a necessity of the antipodal identification that's implied by some, physical principle or not? And, for example, as I was illustrating yesterday, I think that one can at least write down what look like reasonable states which do not have the antipodal matching, or dressed operators for that matter.
Right, but then you have to write down what is the conserved charge and how are...
Yeah. Well, so you just don't satisfy that condition, and that's okay. There's a local conservation law, but the global conservation law is sort of modified in the sense you don't satisfy this relation.
Yeah, so I mean, this is maybe the simplest one, where you just, so this charge is just given by epsilon star f, and so and you integrate over scri minus, and this is the same thing, but integrated over scri minus plus, and so once you identify the epsilons at scri plus minus and scri minus plus, which are the points that go to I0 from different directions, then this follows. Now, if you want to...
Well, no, I think there are field configurations where that doesn't follow, basically.
The other ones that you talked about yesterday, right?
For example.
Yeah, so then when this doesn't happen, antipodal matching, and you still want to say that there is some conservation laws, then you would have to tell me how.
Well, yeah, I think there are local conservation laws, but let me not divert too far. But this is...
I can just complement the answer. So I think that what will happen if you don't have imposed that boundary condition, which is really essential for all the argument, you will not have the triangle because you will not have the Weinberg-Stoff theorem. You will have an anomaly that will appear on the right-hand side of Weinberg-Stoff theorem.
Well, that would be interesting to see. There, from at least from the classical point of view, I think these look like reasonable configurations.
An anomaly related to the fact that boundary condition is violated.
Anomaly in what?
Well, you know, this Weinberg-Stoff theorem is a wide identity of the Kac-Moody symmetry of this, you know, this large gauge transformation. So there will be an anomaly of that large gauge Kac-Moody symmetry.
Okay. Well, yeah.
But
Okay. We should try to figure out what that means. But yeah, okay.
Yeah, so that's the relation between these two things. So this is a large U1 gauge asymptotic, so that's why it's a large U1 gauge symmetry. It gives rise to this conservation of charge at every angle once you impose the antibodal matching. Then for gravity, so this would be the, so you can also write down conservation laws here. Here we're talking about BMS supertranslations, which are these diffeomorphisms here. And you can define a charge corresponding to this parameter related to supertranslations. I could be much more pedagogical and go into much more detail, but 15 minutes are not enough to do that. So maybe if there are questions at each point, please ask. So again, you can write down conservation laws, and this charge here will come from a subleading term in the metric, which is called Bondi mass. So you integrate, instead of integrating epsilon star f, you integrate this function f with the Bondi mass. Then these transformations here have been called superrotations. Again, you can write down a conserved charge. Things are a bit more tricky here. The conserved charge here comes from integrating over what's called the angular momentum aspect with this vector field y. And again, you can write down conservation laws. And now these conservation laws are what is related to the soft theorems. So the connection between these two corners is the Watt identity. So you can relate quantum scattering amplitudes to each other when there's a symmetry. And when you write down the Watt identity, that's associated with these conservation laws. So essentially what you do is you wedge here the commutator between a conserved charge and the S matrix. And then you will find that when you do this here, when you compute the Watt identity of this symmetry, you will exactly produce these soft factors, first respectively electrodynamics and the leading soft graviton theorem and the subleading soft graviton theorem. And so what's related here is energy is conserved at every angle. That corresponds to this leading soft photon theorem. Sorry, that was the charge. Charge is conserved at every angle. Energy is conserved at every angle. That corresponds to the leading soft graviton theorem. And angular momentum is conserved at every angle. That corresponds to the subleading soft graviton theorem. One could go into much more detail about all that, but I guess there is no time. Okay, what else? Yeah, and then just very briefly about the memory effect. So let me just say this in words. So for electromagnetism, the memory effect that's related to asymptotic symmetries and the soft theorems would be that you give relative phases to adjacent charged particles. So that's the sort of more physical effect of these symmetries, or respectively the soft theorems. For gravity, you give, if you have a set array of detectors and you shoot a gravitational wave through, you will get a relative displacement of these detectors. And for the subleading soft graviton theorem, you get a relative delay of counter-orbiting objects. And I think Geoffrey will say a bit more about this. So, yeah, that's in a nutshell these three topics related. Are there any questions, or is everybody familiar with this?
Comments or questions? So maybe what Geoffrey will relate, bring us back to black holes, I think, and then maybe we can have some more discussion about what this means in that context.
Yeah, so I'm trying to lift the other one, but I think it doesn't want to be lifted.
This one you want to go up?
Yeah, it only goes down.
No,
I mean, I tried every combination.
Oh.
Ah, okay. Just slow.
There's a time delay. A Shapiro time delay. Okay. And then this.
So this was just sort of old stuff and in part new stuff by people in the audience. How much time do I have left? Because I want to talk about something that I did as well.
Oh, well, it was supposed to be a total of 45 minutes for the three. And then plus discussion.
So is the answer no?
How long?
So I wanted to mention briefly conformally soft particles and flat space holography,
So
which,
what do you need time-wise?
well, I can just give the gist of it in 5 minutes.
Okay. Yeah, 5 minutes.
Thank you. Okay, so I want to mention this because I'm excited about it, and maybe at the end of the day, if there is really a flat space holography, maybe it will be able to say something about black holes and the information paradox. But that's at the very far end of the way. So let me just mention briefly what it's about and what you can potentially learn. So in 4 dimensions, the Lorentz group is SO1,3 or SL2Z. And so the question, if you want to ask, is there a holographic structure of Minkowski space, is first of all, you have to understand what the symmetries are. And you have to ask where a potentially holographic dual theory should live. So in Minkowski space, the natural thing would be the conformal boundary, which is Scri plus and minus times the sphere that you don't see here. So it's what's called the celestial sphere. So it's a line times a sphere. So this would be the natural holographic screen. And so what are the symmetries there? So in 4 dimensions, the Lorentz group is SL2Z, and it acts on this sphere as the global conformal group. And then when you couple it to gravity, and this is also old stuff. People have looked into SL2Z properties of scattering amplitudes and so on, dating back to Dirac. But maybe the new thing is that when you couple it to gravity, the global conformal group gets enhanced to the local conformal group. And so for everybody who has studied ADS-CFT or the CFTs, this looks very promising, and hopefully there will be an underlying dual CFT to Minkowski space. Okay, so conformal group on the celestial sphere. And so, okay, how do you see this? So in Minkowski space, when we look at scattering, we compute the S matrix. And now the statement is that because of this realization that the symmetry acts as the global conformal group, is that you can write scattering amplitudes as correlators on this celestial sphere. So you will have some incoming states and some outgoing states, and now there will be operators inserted at certain points on the celestial sphere, which I denote by Z and Z bar. And those are equivalent. And so the thing here is that we usually talk about quantum field theory in a momentum energy eigenbasis. So we label our states by a frequency and a momentum, and so we talk about plane waves as a basis. And this makes translation symmetry manifest. So it's useful for many, many properties, for many, many questions. But if you want to find a holographic underlying structure, you should manifest the conformal symmetry. And so you need to do the basis change. And so the basis change is that here in the basis where you have correlation function instead of scattering amplitudes, you replace your energy and momentum by the quantum numbers of the symmetry, namely SL to Z, and those are the conformal weight and the spin. And you have to label a point on the sphere. And so then you no longer have plane wave as a basis, but you have what's called conformal primary wave functions as a basis. And so these are solutions to the four-dimensional equation of motions, but they transform under the conformal symmetry. So this is a very natural basis to talk about conformal properties and potential holographic structure. And so the thing that I briefly wanted to mention is, so in this picture we talk about the soft particles, which is when you take the momentum to zero. So let me say this by taking omega to zero, so you get soft particles. And these have universal plot properties. Once you go to this basis, what you actually do is you integrate over all the frequencies from 0 to infinity of whatever scattering amplitude you want to transform. And so you lose the notion of energy. And so in this new basis, which is useful again for holographic purposes, you need to find a notion that is analogous to that of the soft limit in the usual plane wave basis. And the notion that we proposed is that of a conformally soft particle. And conformally soft particle means you take either the conformal weight h to 0 or h bar to 0. And then this gives you sort of the analog structure in correlation functions that you had for the soft structure in scattering amplitudes. So, for example, what you can do is, if you talk about asymptotic symmetries, in the usual picture, you talk about shifts in the gauge fields, so that gives you the memory. So either the gauge field in electromagnetism or the gravitational data in gravity. Once you do this basis change, and you start with a four-dimensional solution to the equations of motion that transform as conformal primaries, what you will get is a full solution to the bulk equations of motion, which, as you take it to Scry, where you have the sphere that is parameterized by Z and Z bar, you get currents that generate for you this asymptotic symmetry.
Sorry, can you say again, what is H? Full H?
Oh, H is the conformal dimension.
Yeah, but what is it in terms of momentum and spin or something? What does it correspond to?
It is the quantum numbers of the SL to Z. So on this side, you label states by these things, by frequency and momentum. On this side, you label states differently. You no longer get to talk about energy because you integrated over it.
There's some integral transformers later.
Yeah, so this is a Mellin transform. So this is, in a sense, the dual variable to the energy. So here we have plane waves. So let me take a plane wave here.
I guess what I'm wondering is, in a scattering experiment, I mean, are the waves at infinity going to satisfy your conformally soft condition?
What do you mean the waves at infinity?
Well,
So I take a plane wave, I do a Mellin transform over it, and then I get something else. So I do this Mellin transform, and then I get something that is familiar if you do ADS-FT.
I'm not asking about any technical detail. I'm asking about the general framework. Are you claiming to be able to recover some dual description of the entire S matrix for all possible instates? Or are you restricting somehow to some very small subclass which has conformally soft asymptotic states?
No. So this is not a statement about soft stuff at all. It's a statement about general energies or general dimensions.
So why can you restrict to conformally soft?
I'm not restricting anything. I'm just saying. So there is this, do a basis change, then you get a different description of your S matrix in a conformal basis, where it looks like a correlation function in a 2D theory. Now, and the only thing I'm saying is that the soft limit in scattering amplitudes and all these soft theorems and everything is mimicked in this new basis by a conformally soft limit because you don't have energy anymore.
One other very basic question. The picture of the S matrix, there's kind of two celestial spheres I see, the incoming one and the outgoing one.
Yeah.
Whereas you have only one on the right-hand side of the equation.
But okay, I drew a position space picture, right, to draw the scattering, but we also usually talk about the momentum basis, right? So you don't talk about the point in time where the particles came from. So here, so the okay, let me say this. So there are regions on this celestial sphere that I associated with scry minus, and then there are regions that are associated with scry plus.
One way is positive and negative frequency. So
Yeah.
that's what, I guess that's one way you could divide the two in and out. Is that what you're doing?
Yeah.
Okay.
Yeah. Anyway, there's much more to say, but 15 minutes are a short time, so.
Okay, and we're past that. So let's move on with Geoffrey. Can you do the microphone? There, thank you.
All right, so let's go back to gravity and black holes. So I think for further discussion on the black hole session, I should present the conjecture of Strominger on how to resolve the black hole information paradox using soft hair. I think that's important. Everybody has in mind what is the conjecture, the exact conjecture. So let me start by that, because then we can discuss about it in the afternoon. So the main idea of the proposal, if we look at the emission from the outgoing states after black hole collapse, the idea is that there will be a mixed, there will be a hard sector and a soft sector, and there is a correlation between these two. And the outgoing state is really a sum with various coefficients of direct products within this hard sector and soft sector. And alpha here labels the hard or finite energy states. So omega finite. While this is a soft sector where omega goes to 0. And the conjecture is that there is an orthogonality of the soft sector. So where the label labels the hard particles, the hard modes. So that's the conjecture, and it's a very strong conjecture. It means there is a bijective correspondence between the hard modes and soft modes. So there is not only a high correlation, but there is really a crucial correlation between hard sector and soft sector, which would allow to purify the outgoing Hawking radiation. I think that's, yes?
Sorry, but I mean, if you have this relation, doesn't it mean that you don't have a tensor product structure of the Hilbert stuff? Tensor product structure means that I can pick anything from one factor and anything else from the second factor. But isn't that contradicted by...
Well, maybe this is a way to write it, but...
well, in other words, when you say you have a tensor product structure of the Hilbert space, it means that there exists some states where I cannot have this correlated choice. But if every state has this correlated choice, doesn't it just mean that the operators that act on the soft sector are just rewritings of it? In other words, it isn't that physically true. Like you can compute, you know, like the memories are functions of a hard variable.
Right. Yeah.
Independent.
Right. So you know this. I don't know exactly what this is. What the two key formula of Strominger, you know, of his proposal. I don't know exactly what he has in mind in terms of field of spaces, but I think the main point of the conjecture that there is this correlation for between all possible hard states and soft states. I think that's the main point. Now, the details of the Hilbert space structure, I don't know exactly what would be the yes.
I don't want to really engage with the conjecture itself, but I would completely disagree with the notion that that has anything to do with black hole information paradox.
No.
I mean, one is starting out with a statement that the information is coming out. It's then very easy to forget some of it. I mean, if you look at the Hawking radiation coming out of the black hole and you're not very careful, then of course you're going to see a mixed state. But once you say that the information comes out in whatever form, the firewall argument applies. You have to explain how an infalling observer gets in, and that's the thing that is actually zero engagement with that question in this proposal.
Right.
So it doesn't really matter, you know, that there are a billion ways that I could lose information if I'm not careful. Once you say that it's coming out in any form whatsoever, you have this problem.
But maybe, I mean, if you take this the viewpoint that you are okay with having a firewall for important observers, but we're just talking about...
I think we should all discuss this because I don't want to claim that I believe the conjecture, that I want to push for it. I just want to put it on the board so that we agree that this is the conjecture. But I think we should all discuss that in the afternoon. I should present the rest, otherwise I will never be able to make it. But I agree with you. But here the conjecture is that there is all the information is out of the black hole in the infrared sector. So all the information of the black hole is outside already. So, but then we should discuss all this. All right. So that was the first point in 1 minute. Now the second point I just wanted to say about memory. Let me just say the simple thing about memory for the case of gravity and for the leading memory. So the idea is that there is a field defined at Scribe plus, a canonical field of the gravitational field, and you can define its value in the past of Scribe plus and in the future of Scribe plus. And the difference between these two is a function of all the hard energy processes that went through Scribe plus. So it's a functional of hard modes going through Scribe plus. And the structure, the funny thing about this is that this canonical field, if you define it, it also transforms under super translations. So if you apply super translation, it will also shift this C. So this is how you find the correspondence between super translation and this memory. But what I really need is this. So this is what is sometimes called a soft hair implant. So I just want to clarify the terminology. By doing some finite energy processes, you will update this difference of memory fields between the future and past of Scribe plus. Okay. And then the related thing is that the charge associated to the translation, as Andrea explained, there is a conserved charge with some current, and the charge at the future of Scribe plus and at the past of Scribe plus is equal to the current of Scribe plus, and that's called the soft charge, and that's called the hard. Okay, so just the terminology that people use. Okay, so now let me go to the main topic. So how could there be correlation between the soft and hard sectors? So we heard from Gordon that there is correlation. There is a correlation between the soft dressing, soft factors, and hard particles. So how does it work? What exactly are these conservation laws? Yes.
This might be a misguided question, but a feature of Scribe plus is that only null rings reach there, right?
Yes.
I mean, some hard particles are massive.
Right.
Never get there.
Oh yeah. So here, I mean, only massless field. Hard in the sense of all the massless energy, all the massless field that reach Scribe plus. So it can be gravitational waves. It can be null matter or changes of Bondi mass that reaches there thanks to update of the Coulomb field caused by any finite energy matter or finite mass matter inside, but the Bondi mass will change infinity. So that's the ordinary memory, for example. It's still created, but it's still induced by ordinary matter. Okay, so let me go to the main point because otherwise I will never reach there. So, the one thing I would like to say is that there is the only correlation really that arises is from this conservation law at spatial infinity. So this antipodal map of charges at infinity, and is the only known conservation law that allows for this correlation between hard and soft sector. So in that sense, it's very crucial to see what are the consequences of this and if there is a way to violate it, because it's possible to violate it and all this goes away, I would say. So this is really the crucial point. So if we accept and we can debate this conservation law of spatial infinity, this antipodal map of charges, which then can be rewritten in terms of the Weinberg-Soft theorem, then my question is, what exactly is the hard part, is the hard, the information, which information of the hard sector is encoded in these soft modes? And to answer that question, let me draw a diagram. Let me go back to the original Hawking computation. So if I go back to the original Hawking computation, we have, let me just define, so we have this retarded time u, advanced time here. And as you know, we're doing collapse. There is a specific limiting time, V0, which is the limiting time here, after which the null, ingoing null matter will just go inside the black hole. And before that, it will be, so probably I should draw it here. Well, the horizon will be here. So, and before that, it will just scatter and be sent to null infinity. And the relationship between these null rays at scribe plus and scribe minus is this this exponential or logarithmic relation, this one. So that's the key equation of Hawking's computation. And there is a finite shift which labels this limiting retarded time, and there is this exponential relationship related to the surface gravity. So now this is for spherical collapse. If you have a non-spherical collapse, then depending on the position of the light of the incoming null ray, this shift will depend on the angle. So the specificity of the non-spherical collapse with respect to spherical collapse is encoded in these two functions here. So it looks like a shift of u. It looks like a memory, and it's more than an analogy, because you can just map this problem to Unruh, the Unruh case. So if you map this to Unruh, so I consider now my accelerated observer, and I consider now a setting where you have two shock waves. So you have Minkowski spacetime with two shock waves. And as Gerhard was explaining this morning, once you have shock waves, what shock waves do is that they apply a shift. They apply a shift. So this shock wave will shift u with something that depends upon the form factor of the shock wave. Same for a shock wave, an outgoing shock wave. There was a logarithm. So there was a logarithm for the talk of Gerhard, but it comes from the wave equation. In general, it depends on the details of the matter. So it's an arbitrary shift depending on the form of the stress tensor that you put there. So in this setup, actually, you can compute the Bogoliubov coefficients between scribe plus and scribe minus. And they have exactly the same structure as the Bogoliubov coefficient of the collapse, with taking into account the non-sphericity of collapse. So that's the point I would like to say. So the non-spherical collapse can be mapped to the problem of the Unruh, or the accelerated observer, well, let me just say Unruh, with these shock waves. And I do this what I would like to call these super translations. And so I will just write down what this Bogoliubov coefficient look like. So there is the standard, classical transmission coefficient, the spherical collapse, which is the Hawking standard results. All right. I just put it so that for definiteness. So that you have it in mind. Okay, the standard coefficient. And then the factor coming from the non-sphericity of collapse. mixes the different angular modes, the LM modes. And the exact equation is, it was not written in the Hawking paper, and it was, as far as I can tell, was not written anywhere, but they're very simple to just derive it. So it's this one. And I think that's just the key equation I wanted to write down. All right. So, when you have the non-spherical collapse, the final Hawking emission will not be changed because this factor, when you average it out over all the possible ingoing states, it will just disappear. It will just give you a 1. But the fact that it's there, well, here you have, you see that the influence of this non-trivial supertranslation in V and U of coming from the specificity of the matter mix up these modes. This factor is exactly the one you find in the Roux case with supertranslating shock waves. So it's exactly an analogy. And the importance of this is that it will change the properties of squattering. So if you have, in the Hawking radiation, there is no, you start with a vacuum state, and you obtain your thermal state, your thermal radiation. If you start with one particle states, this factor will start to matter. And so the properties of squattering will depend on this supertranslation, this factor V. So I think that's interesting feature that from the point of view of infinity here, this supertranslation, soft error implant, if you want, the finite supertranslation induced by shockwave shows up in the Bogoliubov coefficients. It doesn't change the Hawking spectrum or the Andrew spectrum, but it changes the properties of squattering. And to finish, I would say that this shows that it's a very little information about the collapse that is encoded there. Very small information because it's only basically this information, how light rays look at very large distances between past and future and infinity, and there is not enough information to know all the distance of collapse. So even if there is a correlation between all these shifts of U and V, which is this supertranslation type shifts, and even if it's correlated in the soft hair, it will never give you enough details about the collapse. It would only give you a very small information. That's the main thing I want to say. Yeah.
Let's first thank all three. Speakers, and then let's open it up to discussion of the points that were made, and in particular relevance to black holes. I think is an interesting point of discussion. Comments, questions?
Well, just on the very last thing you mentioned, you're looking at it within the context of a free field on a background, right?
Yes, so here it was, it's really quantum fields on the background, and I was using the Fock space basis, so I was not using the dress states, but I'm looking at the sector, so it's a Fock, to do that. So it's the Fox, I'm using quantum field theory in curve space in Fock space basis, yes.
So how do you anticipate that your conclusion would change if you took into account interactions in the field theory?
Interactions in field theory.
So that you don't just propagate free fields backwards through the collapse to scry minus.
So the interactions,
among other things.
Well, this relationship is an asymptotic relationship between the light rays here and here, and I suspect that all the interaction die off at infinity and will be included in some change of what you will mean by these shifts. But this relationship will still be true. No,
it's a geometrical relationship.
That's
true, but what it has to do with quantum fields is another question. If they're interacting fields,
yeah.
Correlation functions. A 2-point function doesn't propagate independently of higher point functions. So Basically, but you're treating this as if all you had to do is solve the wave equation,
Right.
which is not the case for an interacting field.
Right, right. So here it reduces also to null jersey because of the geometric optics approximation of waves, where they all oscillate and then they reduce it into something classical. So I'm not totally sure how to answer your question, but it's here. I mean, it is maybe the simplest thing to discuss it. Just Unruh case. So here is just flat space with two shock waves, and here I looked at just a free scalar field to compute the Gorbaliov coefficient and obtain this, and then to see that the Unruh radiation is not affected by these supertranslations, and to see that scattering is affected. Now, if maybe your question would be if you look at the interacting scalar field in this setup, what would be the difference? So it's known that Unruh radiation is not affected by interactions. If you take an interacting scalar and you look at the Unruh radiation, is not affected. So I would expect some similar argument will apply here. You would be able to.
Well, sorry, it's certainly very affected. It's certainly very affected. It's just that it's still a perfectly thermal state, but it's thermal with respect to a different Hamiltonian that includes interactions, and so its properties can't be inferred from the same geometric optics type analysis.
Yeah. The basic answer is that I don't know because I didn't do any computation for interacting theories. It would be.
Sure. I had maybe two comments / questions. First, a comment on the formula you wrote down at the beginning with the correlation between the hard and soft parts of the state. It's related to what Daniel said. I think, and this is what I was arguing yesterday, that yes, you can write down a state with a particular correlation between the hard and soft part, but you can also consider other states which have, a different soft state correlated with the same hard state. There are many, in fact, right. And that's how you get something like a tensor product, right, where you have independence between the hard and soft part. So as long as you don't have a necessary correlation, then you can't use that correlation.
Right, I totally agree. So, so it always go back to the basic question: do we accept the boundary condition at special infinity or not? So I think it's the only question. Can we define a theory where at special infinity there is a different boundary condition than the one that was proposed? Because
you mean the antipodal?
The antipodal map. Because if you then relax that, everything goes away. There is no more correlation.
Well, I'm not sure if everything goes. I'm not arguing you throw out Weinberg's soft theorems or something like that. You can use states where you have the correlation, but you can add stuff on top of them, I think, without the correlation.
Yeah, I agree with you. I mean, it would be very interesting to find out the structure for more generic boundary conditions. So one thing I can add is so in the case of gravity. So this antipodal map between scribe plus and scribe minus amounts to a parity condition at fixed time. And that parity condition was usually imposed in the classical gravity literature, by Ray J. And so there is very old literature on this. And then if you relax that parity condition, at the same time you relax the antipodal map at special infinity. And I have a very old 10-year-old paper where you can see that then what happens is that there is an anomaly appearing in the action, breaking this super translation invariance. There is some structure that appears there. And so it would be interesting to see maybe, I think this is why I was saying anomaly, because I think there is a structure appearing and that should bring some anomaly to this Weinberg's theorem. I think
well, it'd be good to look at that more closely. That's on. You had a comment.
Just a quick question about what you said. I mean,
this one here. Thanks. I mean, when you say to relax that condition, you mean replace it by a different condition, or you have no condition?
No condition, yeah.
And but then isn't the evolution problem not well defined? I mean, even classically, like how do you decide what is the soft mode on scribe plus? Isn't it just undetermined variable?
So the thing is that the soft mode is with Weinberg.
I mean the exact zero mode.
Right. So Weinberg, in Weinberg's soft theorem, there's only one linear combination of the two helicities that appears in the soft limit.
if you, and so it means that there is a reduction from, there are 2 degrees of freedom, and you get reduced to only one soft mode. So the thing is that if you now relax the condition, there would be two different.
I think my question was more elementary, and not so much about the soft theorem, but just the well-posedness of the classical evolution problem. I mean, so if I do a pure gauge transformation, which is the exact zero mode, who can tell me whether or not I am allowed to do this gauge transformation? If I say that I have no matching.
No, I
agree. You're worried about whether or not you can relax the antipodal matching?
I agree with you that
so let me give you, you weren't here yesterday, but let me give you a very simple explanation, and that is the following. I can consider, let's think of this as classical electromagnetism. I can consider initial data for classical electromagnetism by basically specifying E and B. So here's my E and B. My E, associated with a charged particle, is basically concentrated in a cone going out to infinity, with 1 over r squared fall off, finite energy at infinity, etc. That's my E. My B is 0. And that doesn't satisfy antipodal matching at spatial infinity. And so it also doesn't have, it's also a finite energy difference above the, say, Coulomb solution. You have to be a little bit careful at r equals 0. I think you can do that. And so this looks like perfectly good initial data for classical evolution of the electromagnetic field. And so this is going to give some solution. It will have radiation going off to infinity and so on, but it's not clear that there's anything wrong with it. Maybe there is. We need to really understand better, for example, what's happening at Scry. And quite plausibly, I think it also doesn't have antipodal matching at Scry because of the failure of antipodal matching at spatial infinity. So, so this is an example of the kind of thing you can do, and the question is there something wrong with it? It looks like physical data.
So I think.
But wouldn't there be? Isn't there another possible contribution to the charge that's being matched, which comes from something that looks like a pure gauge transformation that you won't see if I just write the E and B field, so I can adjust that to make it obey antipodal matching, even though it's artificial.
That's part of why I explained it in terms of E and B. E and B are physical gauge invariant variables, right? So I can just specify this initial data. It doesn't satisfy antipodal matching, then you can discuss, how we look at it in different gauges and so on and so forth. But at least, in gauge invariant variables, it's pretty clear that this is a configuration without antipodal matching.
So the antipodal is also on the field strength and the curvature. If you want to relax the antipodal map on the field strength curvature, just to answer, I think maybe your point was that you are worried that there was afraid there wouldn't be a scattering problem at all, because there is no matching here between the data Scry minus and Scry plus if you relax everything. I think that was the first question.
I was just worried about the sort of pure gauge zero mode, which you don't detect in the E and B fields.
Well, those ones.
But don't those things contribute to the charges that people discuss? Like when I say the pure zero mode, I mean the thing which is integrated along the whole Scry plus. Doesn't that contribute to this charge? Or, and I thought when you write the formula where you wrote only E and B, you made some assumption about how you adjusted that piece or something.
Yeah, right. Yeah, somehow the other sector, it sounds like having descendants in the sense of representation of the asymptotic symmetries. Like in the CFT, you have a Verma module. You have descendants of your states, which when you apply these large gauge transformations. So, and that sector is not discussed here. So indeed, there could be also that sector which is orthogonal to this memory, where you have this global gauge transformation of all fields at all Scry at the same time, and that corresponds to a descendant of your states. Mm-hmm. And I think that the physics of this isn't clear. If there's if there is a lot of physics associated to this or not, it's not clear. In the CFT, you would say the analog of this would be to have Virasoro descendants of states. Virasoro descendants are very large gauge transformations. And in the consistent CFT, you need to consider the Virasoro descendants of states. If you have a 2D CFT and you don't consider this Verma module, these Virasoro descendants, you have an inconsistency. So, but the analog in gravity, so you have these BMS descendants or these Kac-Moody descendants. I'm not sure if there is what physics is associated to them.
Okay, I see. Yeah, this may be getting off on it. Well, we should probably continue that particular discussion later. But one other brief comment, and that is, I don't think anyone would dispute that, say, if you throw stuff into a black hole, that you can establish some correlation, say, with outgoing things, right? Because there's interaction between the infalling stuff and anything that's outgoing. But whether that's a transfer of all of the quantum information from the ingoing stuff to the outgoing stuff is another matter entirely. And in particular, if you do have arguments that you can have independent degrees of freedom, so to speak, in the black hole that can be entangled with other things, if that's possible, and if you excite those states, then you have your basic problem of information inside the black hole that somehow needs to be transferred out, quantum information. So it's not clear that this story gets around.
I totally agree. Yeah. And I agree with the Raphael comment as well. It doesn't solve the main firewall problem or how information could come out. I agree.
I guess those sorts of proposed solutions which have that the entanglement of the outgoing radiation is entangled with something else, whether that be soft degrees of freedom, or in Gerard's case, whether it be some other area of space-time. I think they seem to all have that problem that if you have some entangled other people have noticed this about the Hawking proposal, but that if you have stuff which is entangled with the outgoing radiation for some input states, then there must also be, then superpositions of those states are also valid outgoing states. And if I can have superpositions of entangled states, then there is one which is not entangled. In other words, if your solution relies on some sort of entanglement between the radiation and something, whether it be some other area of space-time or whether it be soft hair, then that doesn't appear to be a solution, because I can always put in some input. There's some input state which will not get entangled. I don't know if that's clear. Just because I can take it, if entangled states are valid outgoing states, then a superposition of those states are also valid outgoing states, where the input state is also a superposition. And so that means that there must exist one which leads to an unentangled outgoing state.
I think Raphael can answer this.
I agree with that.
And I think this is a point that you made and others as well, about the Strominger proposal. So I wonder why it doesn't also apply to
I still feel
proposal.
like the sort of zeroth order reason why it can't work is simpler than that. It's once I say that the information comes out, I mean, we could say maybe we can't observe soft modes, for example. But may I just finish? That would be tantamount to saying that information is lost, because if I can't observe them at all, then in which sense is unitarity preserved? So we're talking about particles which are maybe longer wavelength than we would have liked to deal with, that form a complication in 4 dimensions. But we observe them as part of the out state. And at the end of the day, all we care about is that there is some state, whatever its entanglement structure, which is the out state which has the information in it. And then I can run that back and make the argument that it's impossible for an infalling observer to see the vacuum at the horizon. So the entanglement structure really doesn't come into it. And I think it's an interesting question, maybe for other purposes, and this whole question about Weinberg's soft hair theorem, antipodal boundary matching conditions. Those are all interesting questions, but it's not as if the resolution of the black hole information paradox hinges on how we answer those questions. They're interesting for other reasons, but it plays absolutely no role in resolving the paradox.
So maybe this is just from my confusion, but when you were talking about the product between the hard and soft sector, and then people mentioned that you can choose like any soft, given a hard state, you can like choose any soft state, and therefore like this relation between one soft state and the other can't be like set fixed. But as Gordon mentioned in the first part of the talk, also like if you, in the point of view of QFT, if you want to cancel infrared divergences, you have to fine tune the soft states with respect to the hard state, and I think that gives you like a one-to-one map between the hard and soft. This choice is not like unique, but there's a set of states that you can map from the soft and hard, and I'm not sure if you can like do that arbitrarily. So, yeah.
In response to that, Gordon or you give me your favorite soft dressing of a particle, and you're going to send in only particles with that dressing. And I'm going to ask what happens if we do scattering, where you send in that dressing on those particles plus some extra electromagnetic radiation, okay, which has a soft component. And I think you can do that.
And I think, yes, I haven't done this computation, but if you want to like send in radiation along with matter particles, then I think you should also address the radiation, the photons also.
Not necessarily, well, not in electromagnetism, because photons don't carry charge.
Okay, I'll think about this and then come back to you.
Other comments or questions?
I guess just a trivial comment that this states that you're suggesting, it has a features that if you evolve it forward or backward in time, it never looks like a set of free, widely separated particles. And in the S-matrix theory, usually, whenever if you take let's say you start a bunch of separated photons or electrons or whatever with a Coulomb field, then it will not have this feature at infinity. So a little bit looks like violating this condition, something like adding a source, some kind of source at spatial infinity. I'm saying that let's say you start with a bunch of free electrons or photons and then let them scatter. If state ever looks like this, at time zero you will not have this picture that you suggested, because if you said if you relax it, then the radiation will come out and it will become, but it will, at arbitrary late time you will have a region where radiation is still coming out and it looks like a non-equilibrium state, which does not look like a set of free particles. I don't know if it's relevant.
Yeah, I think we can try to draw a picture of what what it does look like, say, as an out state or an in state, but we probably shouldn't do that right here, right now. But let's try to do that. Other questions? Comments? Controversy?
This was just a question for Gordon. You mentioned that there were, that I can consider mixed states as being the extremal states or as the pure states?
Yes, I mean mixed states is incoming states.
As incoming states. And is that, can I think of that just as like a group averaging over some symmetry? Is that a way to think about it, or?
Yeah, in a way, the statement in the original KLN theorem had to do with averaging over degenerate states. So the idea is that a charged particle plus a soft photon, and so on, are all actually degenerate states. They have the same momentum, same energy. And so to properly do degenerate perturbation theory, one needs to, in some sense, diagonalize the Hamiltonian in that set of all degenerate states. And the only way to do that perturbatively, according to them, is to do what is the equivalent of send in have the incoming state be a density matrix. which really means almost giving up on pure states altogether, at least in theories of massless photons and gravitons.
Okay, well, I think we should. Oh.
Yeah, we have time left. I'd like to ask something.
Oh, okay, sure.
So, since Andrea got cut off at the end of what she was talking about, I was wondering if she had anything more to say about how far have you taken it already, and what do you anticipate could be done with these correlators on the celestial sphere? I mean, are you really proposing, or have you already seen that the S matrix can be formulated as a conformal field theory?
No, so definitely not to that last question. And there's not so many people working on this, and this program hasn't gone that far yet. I can tell you what kind of things have been done. So for example, in this conformally soft limit, we have identified some conformal primary wave functions that are related to the soft photon current and the stress tensor for, so there's been work about a 2D stress tensor for the gravity, and this shows up as a conformally soft conformally primary wave function of spin 2. And then there are some sort of strange looking currents in this theory. So one of them is that, so if you do the canonical formalism and you look at symplectic products, like in a phase space formulation of P and Q, you would like to have a partner to each mode. And so, for example, the partner of the soft photon mode or the leading soft graviton mode is some new mode that doesn't naturally appear in this conformal primary wave function basis, but it's some shock wave, some sort of new solution to Maxwell or linearized gravity. And in particular, for the leading soft graviton mode, it has funny conformal weights. And if you look at the OPE of what's been called super translation current, which you can get as one of those primary wave functions of spin 2, it shifts, if you look at the OPE between this super translation current and an operator of scaling dimensions h and h bar, it shifts the scaling weights by 1/2 for both h and h bar. And a question is whether this OPE, this funny looking OPE, gives constraints on the S matrix in the conformal basis. And then people have looked at collinear limits, so not only there's recent work on conformally soft limits in scattering amplitudes where you also see a factorization property. All of the things are a bit tricky because once you go from scattering amplitudes in the usual basis to the conformal basis, there's a lot of delta functions that appear. So you always have to work with distributions, and it's subtle. But there is some factorization property, and then people also looked at collinear limits and got the OPE for certain operators in particular, from Young-Mills scattering amplitudes, like MHV amplitudes. You get the OPE for spin 1 fields. And okay, what else? So there's also interesting work that shows that in the opposite to the conformally soft limit, where you take sort of the imaginary part of this conformal dimension very large, you see that the string worldsheet looks like the celestial sphere. It's also an interesting
Which
fact.
string?
If you do string scattering amplitudes and you transform them into this conformal basis, and then you take the limit that the dual variable to the energy becomes large, then the string worldsheet looks like the celestial sphere. So that's interesting. Yeah, and so so one thing is that in the usual basis we have translational invariance, and so this is useful for certain questions, but then this sort of new basis may be useful for other questions, and so it's an open question what you can do with it, how far you can take this, but there's lots of basic things that haven't been worked out yet. So
just one comment, that it reminded me of something that Lionel Mason once told me about, which was, I think, scattering of gravitons in classical GR formulated in terms of a mapping from scry minus to scry plus that should somehow be compatible with whatever you're trying to construct. It would be an example of one of those scattering processes. So it might be useful to look at or talk to him to see what it was I'm not sure if it was published or not.
okay.
I think it was.
Well, maybe you can tell me more later.
Okay, well, I think that's a good place to wrap up. So we will reconvene at 2 for our black hole information discussion, and let's thank our panel once again, and good luck.